Welcome to the physics class for November the 19th. Before we get started, let's talk about a couple announcements. First off, quiz 6C is now unlocked and available for as many retakes as you want until you get a perfect score on it. Except that although Canvas will show that you have a 10 on it once you get a perfect score, when I transfer the score over into Aspire, I'm only going to transfer it in as a 9 if you did it after the deadline. But nine's not bad. Okay, also tutoring. I think we have everything nailed down for tutoring, and I sent you an email, which I hope that you received. So the plan is that there is going to be one tutoring Zoom room where all tutoring is done in the same Zoom room, be it physics or chemistry or math or English or whatever. It'll all be done in the same Zoom room. And there will be an adult AIMS staff member who supervises it, but she won't be the one that does the tutoring. There will be tutors there. And for physics, it's going to be a couple of the students who are in the U of U physics class who are really good at physics. So they can definitely help you. So they will be there in that Zoom room every Tuesday and Thursday right after school from 3:45 until about 5 o'clock. And also on Fridays from 11 o'clock until about 12:30. So they will be there to help you take advantage of it. AIMS is paying the students to do this tutoring, but they're only going to do it if people actually take advantage of the tutoring. If we find out that there's not very many students showing up asking for tutoring help, AIMS is not going to keep doing it. So this is definitely a use it or lose it situation. Definitely show up to the tutoring sessions. If you did not receive an invitation in Canvas to this new class, so they created it as if it's a class in Canvas, and it's called the tutoring class, and you should have received an invitation to it. If you did not receive an invitation, then send an email message to the person that I listed in the email that I sent to you, Adasa Pasquale. I gave you her name and email address. She's the staff member who's going to be supervising things. So if you didn't get an invitation to the Canvas tutoring class, send an email to her and she'll take care of that. Now, I am doing my Zoom office hours tomorrow. As you know, I can only do it every other week because I've got the U of U physics class that meets every other week that I have to take care of. But tomorrow is a day when I am available to help you guys. So from 9 o'clock until 10:30 tomorrow morning, I will be here in this Zoom room to help anybody who needs help. And then soon after I log off from there, then the tutoring room will open up separately. Don't forget that this coming Saturday is Engineering Day. We've talked a lot about that in the past, so I don't need to remind you how that works, other than just say you can get extra credit for attending. And then also, I trust that you guys know that the schedule next week is weird. Monday should, in theory, be an A day and and Tuesday be a B day, but for some reason they're swapping them around. So Monday is going to be a B day instead of an A day. Tuesday will be an A day. And then we're going to finish up chapter 7 today. So if I wanted to, I could, in theory, give the midterm exam next week, right before Thanksgiving. But based on what I'm seeing in your quiz scores and your homework and stuff, I'm thinking that you guys would probably appreciate having a day of review. So what we're going to do is next week when we meet, it'll be a full day of just review only. No new material, just pure review. And then the test will be right after we come back from Thanksgiving. Okay, I think that's all the administrative stuff. Are there any questions about anything that I just went over? Okay, so Calvin wants to know, are we doing a meeting after school today? And the answer is there will be a tutoring session, not in this Zoom room, but if you go through Canvas to get into the tutoring Zoom room, yes, there will be one after school today. And I don't see any other questions. Okay, well, let me jump into the answers to last night's homework. There were quite a few of them that were not in the back of the book, so I broke them up into two parts. So here's the first set of problems. I'll give you a couple minutes to look these over. And then once you tell me that you're ready, then I'll show you the rest of the problems, problems 11, 12, 13, and 14. So same as the normal procedure here, if you could only see one of the problems worked through, which problem would you want that to be? So please type into the chat box. Everybody vote for which problem you want to see worked through. And it can be anything from 6 all the way up to 14. Yeah, so yes, there are more to show you. I mean, if you see, here's the answers to the other ones, but there's too many to fit on one page. So I'll just show you these for a couple minutes, and then I'll switch and show you the others. Are there no problems you guys want to see? I'm not seeing anybody voting for problems here. Were they so easy that you don't need to ask questions about them? Okay, so I'm seeing a couple people asking for number 8. It looks like 8 is definitely the winner. Okay, so 8 is what we'll do then. So let's see, what is it asking in problem number 8? Okay, so we got 2 packages that are 35 centimeters apart. All right, well, this one should be pretty straightforward. This one's just using Newton's law of universal gravitation. So I can do it right here on the same page here. I think it was not going to take much. So the force of gravity is equal to big G times the mass of the one object times the mass of the other object divided by the distance between them squared. And so that's 6.6. Let's see. I might need to move. Hopefully, I'm moving my face over so that you can see this thing. 6.67 times 10 to the negative 11th. That's big G. The mass of the one object is, oh, they're both 15. Okay. So one of them is 15 kilograms and the other one is also 15 kilograms. Now, if you got a different answer than I've got up here, it's probably because the units, the distance they give you is in centimeters. Whenever you're using an equation that has a big G in it, the numbers that you put in absolutely have to be standard physics units. And for distance, the standard physics units is the meter, not the centimeter. So we cannot put it in as 35. We have to put it in as 0.35. Okay. All right, so if you do that, this is the answer you should get. Are you guys getting a different answer than I am? So if you guys got a different answer, I'm willing to bet it's probably because you put the number in centimeters rather than meters. So, okay, so Austin is saying that he did get a different answer. Okay, well, tell you what, let me take a second and do it right here. So big G is 6.67 times 10 to the negative 11. And the mass of the one is 15 kilograms. And the mass of the other is also 15 kilograms. So I'm going to divide that by the distance, which is 0.35, but the distance has to be squared. Okay, I get 1.22 times 10 to the negative 11, or 7, I mean. 10. Yeah, I'm getting the same answer that you see on the screen here. Okay, so let's call it good on this one then. So now I'm going to show you the other page. All right, so here are the rest of the problems that you need to see. And I think we got enough time here. If you want to see one more problem worked through, I'm willing to do that. We can squeeze one in. So everybody gets to vote another time. All right, so I see somebody voting for 14. Let's see a few more people vote. If there's only one person that wants to see problem number 14, I'm not going to do it. I need more than one people here. Okay, now, okay, so we are getting more than one. All right, so it looks like 14 is one. Yep, okay, it's definitely 14. No question about that. Okay, so that's one we'll do. 14. We want to use the data for Mercury in table 7.1 to find out the following. Okay, I'm thinking we're going to need to open up a whiteboard for this one, because we're going to have to do a little bit of drawing here. Okay, so first off, let's draw a picture. So problem solving strategies. My favorite problem solving strategy by far, draw a picture. It will help you a whole lot. Okay, so here is the planet. Here is the satellite in orbit around the planet. Okay, and so they're saying that the orbit is 260 kilometers above Mercury's surface. Now, if you're having trouble, I can think of two things that may have gone wrong. One is you need to recognize that when they say 260 above the surface, they mean from here to here. This is 260. It is not the distance from the center. Okay, and the equation that we want, the equation that we're going to use to solve this, the value that we put in for r has to be from the center of the planet up to where it is. So this 260 is only the surface. All right, so one thing we're going to have to do is we're going to have to look in the table, and we're going to have to find out what is the radius of Mercury. So when I look in the table here, table 7-1, it tells me that the average radius of Mercury, so that would be this right here. Actually, I'll tell you what, let me draw it up here. Just okay, so this distance is 2.44 times 10 to the 6 meters. Okay, all right, so if you put in 260 into the equation rather than adding this, then that would explain why you got it wrong. But the other thing that that probably messed some of you up is that this 260 is kilometers, not meters. So we have to rewrite that as 260 with 3 more zeros, so times 10 to the third. So the number that we put in for r then is going to be 2.44 times 10 to the 6 plus 260 times 10 to the third. That is the number we need to put in for r. All right, and now what equation do we put it into? Well, let's come here. Hang on a second here. Okay, so these are the equations that were used for all of your various problems there. So in this equation, in this problem here, part A, they want to know the speed of the satellite. All right, so that means we're going to use this equation right here. Now, where it says ME, well, that's not going to be, because this is talking about Earth. So we want the mass of Mercury, but we can get that from table 7.1. This R here has to be the R that we just came up with, okay? It is, R has to be the distance from the center of the planet to the satellite, not the altitude of the satellite above the surface. So if you guys got different answers, that's probably the reason why. Okay, and then for part B, they want to know the period of the satellite. Okay, so again, this R value here has to be this R, not this altitude. And then the mass of the Mercury, we can get that from the table. Now, the T here, okay, so remember, this is really important. I want everybody to pay close attention to this. Anytime that you are using an equation that has a big G in it, that equation has the things that you plug into that equation must be standard physics units. Okay, so that means the distances must be meters, not kilometers. The masses must be kilograms, not grams. Now, those of you that are taking chemistry, I can see why you're confused, because in chemistry, the standard unit for mass is the gram. But in physics, it's not. In physics, the standard unit is the kilogram. And then time. What is the standard unit in physics for time? Well, it's the seconds. So when we put these numbers in here to the right side of the equation, the number that comes out the left side of the equation is going to be the number of seconds, because that's the standard physics units for time. All right, so if you got a different answer than I did, well, maybe it's because you didn't realize that the number that came out was in seconds. Okay. So are we good there? We actually need to work on it, or does that answer your questions on number 14? So type, if we can move on now, go ahead and type in yes. But if you still have a question about 14, then type in no. Okay, so I'm seeing lots of yeses. All right. Okay, let's talk about the new material now. All right, so we are going to finish up chapter 7 today. There's not a lot of really heavy new material. It's basically more conceptual and not really equation based. So let's just go ahead and jump right into it, and hopefully it won't take us very long. First thing, what if I wanted to calculate the acceleration due to gravity on some other planet that wasn't the Earth? Now, in theory, I could get on a spaceship, go there and stand on the planet, and then, take an object and drop it and measure the acceleration, but it's not really practical. If only there was some way that we could calculate what it is. Okay, well, let's think about how we do it on Earth. All right, let's say that I have some object here. Let me open up, let me turn on annotation. Okay. All right, so let's say I've got some object and I hold it here and then I let it go. So the only force that's going to be acting on this object is gravity. And so if I do F equals ma, then the acceleration that I get is going to be the acceleration due to gravity, because gravity is the only force that's acting on it. All right, so the force of gravity is going to be m times a. So if the acceleration is purely due to gravity and nothing else, then we can call that little g. Okay, so the force of gravity is m times little g. Now on the surface of the Earth here, we know that g is 9.8. The question is, what would it be on other planets? So what we do is we look over here and we say, well, force of gravity, we have an equation now that can tell us what is the force of gravity on any planet, or even if you're not on a planet, even if you're just near a planet, we have an equation that tells us what the force of gravity is. So we know from Newton's law of universal gravitation, force of gravity is equal to some constant, which we're going to call big G, times the mass of the one object times the mass of the planet divided by the distance from the center of the planet, not from the surface, but from the center of the planet squared. All right, so if the force of gravity is m times g, but the force of gravity is also this, that means that this must be m times g for whatever planet you might happen to be on, not necessarily the Earth. And so this m is the mass of the object that we're interested in. Notice that it appears on both sides of the equation, so it cancels out. So what that means is g for some planet that's not the Earth would be this universal gravitational constant big G times whatever the mass of the planet is that you're nearby, times the distance from the center of the planet to wherever you are. So bingo, we can use this equation to calculate what is G on the surface of any planet or in space anywhere near a planet. Now, let's just do a little quick check. If we were to do this for where we put in the mass of the planet Earth, And for R, we put in the average radius of the planet Earth. We had darn well better get 9.8 as our answer, because if we don't, then we know that something went wrong. So I'm going to pause for a minute. I want all of you guys to get out your calculators and let's do the calculations, and let's make sure that we get 9.8, because if we don't, that means physics is broke and we can all go home, except that we're already at home. Okay, now we're going to need to know what numbers to put in here, right? So where do we get those numbers? Well, I recommend that you guys get in the habit of looking in the back of the book here. So I recommend that you go back here and then flip one more page. And so you get this table here. I want you guys to get in the habit of using that table because it's really easy to find. So here is the table. Now I've got a bunch of scribbles on the screen, so it's hard to tell, but let's see if we can work this out. So the mass of the Earth, okay, so that's right there. So the mass of the Earth is, where did I put my glasses? Looks like 5.97. I'm just going to go with 3 sig figs. That's good enough for what we're doing. 5.97. And then don't forget this is times 10 to the 24. Now we're also going to need to know the average radius of the Earth. And so they don't give us average radius, but they do give us equatorial radius. And hopefully you guys realize that the Earth is a little bit bulged out at the equator. So this number here that you see right there is actually not the average radius of the Earth, but it's the only number we got, so let's use it. Okay, so that's going to be 6,378, but be careful because that unit is kilometers. And we're going to put this into an equation that has big G in it. So we've got to put it in as meters. So what I'm going to do is I'm just going to say times 10 to the third. And so now it's in meters, and this other one here was in kilograms. Okay, so I think we're good now. So let's go back to here. All right, so, and then what about big G? You guys remember what big G is? By now, you should have done so many homework problems with it that you should have it memorized by now. So big G is 6.67 times 10 to the negative 11. All right, I'm looking in the chat box. I'm not seeing any numbers yet. Can you guys type it in? And by the way, type it in a private message rather than a public message. I'm going to sit here and wait until I see a bunch of numbers. I can sit here all day if I have to. You guys not have calculators? Oh, okay, so I'm seeing one number. Okay, come on. You guys should always have calculators. Don't show up to class without a calculator, guys. All right, now I'm starting to see, ooh, 10 to the negative 11. I think something went seriously wrong with your number there, Will. Connor, same with you. How did you get times 10 to the 5th? Go back and recalculate those. So Jackson, your number looks good. Boy, guys, this is really disturbing. We're having so many problems here. Okay, when I see this, what it tells me is that we're having a little bit of calculator problem here. So how about let's do this. Let's open up Desmos and let's all do it together. Okay. All right. So let's go into Desmos. Come on. It's kind of slow here. All right. So I'm seeing 6.67 And then I want to do, yeah, I got too many windows open here. So times 10 to the -11th. Okay. And then that has to be times the mass of the Earth, which was 5.9, what was it? 5.97 times 10 to the 24th. Okay. And then divided by the distance of the Earth, which was, let's see, that was 6,378. So 6,378 times 10 to the third, because we need it in meters, not kilometers. Okay, so, and I need to square that. Okay, so and put a parenthesis there and a parenthesis there. Whoops, wrong parenthesis. Okay, so now let's come over here and square that. All right, and oh, I left off a numbers here. So the distance to the Earth. So you can see why it's easy to make a mistake here. So the distance to the Earth, 6,378. I left out my 3. Okay, there we go. So I can fully understand why you guys have a little trouble with this. It's okay. But if you do it right, you'll see over here on the right side, I'm getting 9.79, which rounds off to 9.8. Okay.
Would that work the same if the 5.97 was up above?
Yes. Yeah. Yeah, I could put that all in parentheses there if I wanted to put that there. Whoops. And then the other one there. Okay, it does. Yeah, once it starts out like this, it's hard to change it. But yeah, it is exactly the same, because let me open up whiteboard. Okay, so if I do 3 times 4 divided by 5, that's the same thing as 3 times 4 divided by 5. Okay, yeah, they are exactly the same. Okay, so that's reassuring to know that if we do this for the planet Earth, we get 9.8. So that leads us to be confident that if we do it for some other planet, we will in fact get the right answer. Okay, so you're going to find that this is going to come in handy tonight. They might ask you to calculate G on other planets. But remember, you don't have to be on the surface of a planet. You could also be, floating in outer space just near a planet, and you could calculate what G would be in that case. All right, now another thing. When you read the book tonight, because I know you always read the book before you do the homework, right? They're going to talk about gravitational mass and inertial mass. And I could just let you read the book, because you guys need to get in the habit of just reading the book. It is not my job as a teacher to spoon feed you. In fact, if I spoon feed everything to you, I'm doing you a disservice. You need to be able to pull information out of a book yourself. But I know from many years of teaching that the concepts of gravitational mass and inertial mass are concepts that are a little bit difficult for people to get. So let me just explain what they mean by the two. Let's start off with inertial mass. So if you look at this picture that you see on the left side here. So let's say you're walking along and you're barefoot and you're not really paying attention, and you stub your toe on a rock. So ouch, it hurts a lot. Okay, now, what if you were in outer space? What if you were an astronaut who was doing a spacewalk and you were doing it barefooted, which I do not recommend. Okay, the human body does not tolerate that very well. But if you could do a spacewalk barefooted, and if there was a rock that was just sitting there floating in outer space, and it's in outer space, so it's weightless, right? So you're doing your spacewalk and boom, you stub your toe on the rock. Is it going to hurt? Well, the answer is yes. It's going to hurt just as much as it would if you were on the Earth, because although this rock is weightless, it is not massless. It still has mass. So if you have a mass and if you exert a force on that mass is going to resist because it has inertia. And the more mass it has, the more inertia it has. And so the more it's going to hurt your toe if you stub your toe on it. Okay, so the mass that we have here in this case, we call this inertial mass. And so inertial mass is what we're dealing with when we use Newton's second law and we say that F equals ma. So if our toe here is pushing on this rock and it's exerting a force, if we could measure the force and then we could measure the resulting acceleration, that would be a way that we could calculate how much inertial mass we have. So let's divide both sides by A. So then F divided by A equals m, and this would be the inertial mass. Okay, and this is something that would work even if there's no gravity around here, you still have mass. Okay, now let's compare that with over here on the right side. So over on the right side, what's happening is we are going to take that exact same rock that we just stubbed our toe on out in outer space, and we're going to take it to the surface of the Earth, and we're going to hold on to it, and then let go. And so when we let go, the thing's going to start accelerating downward. And the reason it does that is because there is gravity. So there's the force of gravity acting on this rock. So in this case, this is gravitational mass that we are now dealing with. And so the equation for gravity, the force of gravity, is big G times the mass of the object times the mass of the planet that you are on or near, divided by the distance squared, where that distance is from the center, okay, to where you are. So this mass here, this is gravitational mass, which is not necessarily the same as inertial mass. Okay, so if we wanted to rearrange this equation and solve for mass, what we get is we get the force of gravity times the distance squared divided by big G and divided by the mass of the planet. That equals m, but this m now is gravitational mass. Okay, now it is not obvious that the inertial mass of some object and the gravitational mass, they don't have to be the same. But it turns out that every time anybody's ever measured it, okay, so if you do an experiment over here where you put some force of a known magnitude and you measure the acceleration and you get a number for what the inertial mass of that object is, and then you take that same object and you measure the gravitational force and you measure the distance from the planet and you take into account the mass of the planet, the number that you calculate here and the number you calculate here always turn out to be the same. So it looks like gravitational mass and inertial mass are the same, but it's not obvious that they have to be the same. They could be different, but the fact that they are the same leads to some interesting conclusions. And so in your book, they talk about it. And again, I don't want to read the book to you, but basically, this is what Einstein spent a lot of time thinking about. Why is it that gravitational mass and inertial mass are the same? And so when Einstein came up with his theory of gravity, the fact that inertial mass and gravitational mass appear to be the same, that played a major role in him coming up with his theory of gravity. Now, one of the questions in your homework last night was, what's the difference between a law and a theory? So let's talk about that because I think it's relevant to this. So let's talk about the law of gravity versus the theory of gravity. Okay, so what's the difference in a law and theory? So a law is what has been observed to always happen. So basically, if we do an experiment where we want to measure the force of gravity, everybody who has ever done this experiment has always found that it follows this equation. It's equal to some constant times the mass of the one object times the mass of the other object divided by the distance squared. This is an observed fact. This is not something that we derived. It's just something that has always been observed to be the case. And everybody who's ever done the experiment has always come up with the same relationship. And so this is now called a law of gravity, because a law describes what it is that is always observed to happen. And so this is what is always observed to happen. So that's the law of gravitation. The theory of gravity, well, that tries to explain why does gravity work? And this is something that I would hope you guys have thought about, and I would hope that it has bothered you. I know when I was in high school, it certainly bothered me. I mean, imagine, here's the Earth, here's the moon. The Earth somehow attracts the moon, it pulls the moon towards it. How does it do that? How does the Earth reach out with invisible fingers and grab the moon and pull the moon towards it? Because, I mean, if this is the Earth, this is the moon, you can pass your hand in between and there's no strings there. How is it the Earth is able to reach out through space and exert a force on some object that's way over here and pull it in? That should bother you. It certainly bothered Einstein. And so in your book, they talk about it a little bit. And like I say, it's not my intention to read the book to you, but Einstein came up with a theory for why that happens. And his theory is that empty space isn't really empty. There's something there. And over the years, people have given it different names. For a while, people called it the ether, but then that fell out of favor. And the current term that people like to use is we call it the fabric of the universe. And basically what Einstein is saying is that if you have an object here that has mass, it stretches the fabric of the universe in the region around it. And it turns out that if you were to map out the stretch, the magnitude of the stretch, it turns out that it's the same as the G field that we talked about just a few minutes ago, the acceleration due to gravity. Like if this is the planet Earth, or any planet, doesn't have to be Earth. If you were to take this G value that we calculated and call it a vector. So what we calculated before was the magnitude of the G, but let's make it be a vector. Okay, so the acceleration is always going to be pointed toward the center of the planet. The further out you go, the shorter the arrows are going to be because the magnitude gets less. Okay, and you go out even further and it gets even smaller still. So if you were to calculate what is G at all these different places around the Earth and map it out, what you would have created is called a G field, or field with a D. Okay. All right. So this is kind of like a force field, only instead of mapping the forces, what we're doing is we're mapping the acceleration. Okay, so this is a G field. So every object that has mass is surrounded by a field that we could map out, and we call it a G field. And it turns out that the magnitude of this G vector is a good indication of how much the fabric of the universe is being stretched. So in Einstein's theory of why gravity works, what he's thinking is that this massive object here, it stretches the fabric of the universe. And so here's the moon, say, And the moon feels that the fabric of the universe over on the left side is stretched more tightly than the fabric of the universe on the right side is. And it's the stretching of the fabric of the universe that causes the moon to be attracted to it. So we're going to talk more about this later. This is part of Einstein's general theory of relativity, sometimes just referred to as general relativity. Okay. And I think the book does a pretty good job of describing that. And so I'll just go ahead and let you guys read the book. Okay. Well, that is really all the new material that I had intended. So Sam is worried that I'm going to give her an existential crisis. Good. That means that I'm doing my job properly. Okay. All right. So you probably want to know what your homework is. Well, you guys, of course, you can look on Canvas and it'll tell you there. But here you go. So finish reading chapter 7, and please read the chapter before you do the homework. And notice that in problems 15 through 21, I'm only asking you to do the odd ones, just because you don't have to do quite so much. But then problems 53, 63, and 94, those are good problems. You will learn a lot by doing those problems. So make sure you do those. Okay. And then, of course, don't forget to take today's quiz, which is online and waiting to be taken. You've got 2 tries. If you can get a perfect score in those 2 tries, then great. But if you can't get it in 2 tries, then you'll have to wait until I eventually unlock it after the deadline is over. Okay, so are there any questions? If not, I'm okay with you guys typing bye into the chat box. Now, we still have a lot of time left. Holy cow, we still got a half an hour left. So you can use this half hour to get working on the homework, take the quiz, put it to good use. But I will also stick around here if you have questions. So you can type bye in the chat box and see you later. Tell you what, if you have a question and you don't want to ask because it's being recorded, here, I'll go ahead and turn off the recording so then you can ask your question without being embarrassed. Okay.